So, are there any questions about what was going there last time?
Yes, I have the question related to the U1 symmetry
Mm-hmm.
and the correlation function for phi phi.
Mm-hmm.
If I do phi into phi plus c, I get something not
Yes, because field phi is not very well defined, and we see that this correlator of phi with phi contains explicitly dependence on the infrared cutoff. In a sense, phi of x, phi of y equals to a logarithm of r squared over x squared, oh, sorry, x minus y squared. So it depends essentially on this r. And so it is actually similar to the computation. So how to see the origin of this problem. So we have this path integral where we have d phi e to minus 1 over 2 pi, integral of d phi d bar phi over d to 2x. And this lives, for example, on a sphere. Or on the complex plane, which is the same. And we can say that this field phi has an expansion. Like, so if you put it on the actual sphere with constant curvature, we will need to add here something like 1 over 1 plus, no, nothing, because it cancels with the contribution from the metric. No. So we will have just this, and the phi will be some sum of Gn phi plus n from n equals to 1 to infinity plus sum over z bar n phi minus n plus plus phi naught. And if you substitute this into the integral, this terms will maybe it's not very good from the point of view of normalization, but for the illustrational purposes, I just want to say that there is this component phi 0, which corresponds to overall scaling of phi. And this action does not depend on phi 0. So there is this, this action, and this S of phi is S of phi n's for n different from 0. And this integral over 0 mod is a separate integral. So when we integrate the product of this exponents, we can write that correlator of exponents is so we can say that it is integral in d phi 0 integral in d phi tilde without zero mod. So that integral of phi tilde over d2x equals to 0. So we separate this field into two parts. So in total it will equal to correlator on this field without zero mode. Times the integral over zero mode d phi 0. And this will equal to the delta function. Of course, there is a question if it is delta function or delta Kronecker. In a sense, it equals this. In a sense, what happens when this when the sum of alphas equals to 0? Like if it is infinity or just 1. But it's some question about normalization. But the general phenomenon is that we have this integral in phi 0 in zero mode, and it is usually divergent. So in this case, it gives delta function. But if we substitute here phi of x and phi of y, we will really need to integrate phi 0 squared from minus infinity to plus infinity. Which is not nice. So it's not variable defined, and it's another illustration why we have this cutoff. But if we live not on a sphere, but on some disk, this translation invariance is broken, and we can compute this correlator. So. So the point is that this field actually is not very well defined. It is better to consider exponentials of it or derivatives, which either don't have this zero mode or contain it in such a better way. So. And also a conformal property. So this field will be different because naively it seems that it has a dimension 0, but fields of dimension 0 should have correlators independent on coordinates. But in this case, it depends on coordinates in logarithmic way, and it is called a logarithmic field, and people study such things from a representational theory point of view. So, so it's not absolute nonsense, but it is some special object. So fields that people usually consider have better properties than this. So. But it mostly plays a role of a kind of a fundamental field. So other fields are constructed in terms of this, and usually we don't have access to field phi itself. So any other questions? Okay, so let me remind what was the main result of the last time. So the main result was that if we have symmetry S that resolves action, infinitesimal symmetry. Which means that this G cat G hat is infinitesimal symmetry. Then the transformation of the section under a deformed symmetry will be the following. So it will be s phi plus integral plus integral d to x d mu epsilon of x g mu of x. So in this g mu is conserved current. So which means that if phi satisfies equations of motion, then d mu g mu equals to 0. Okay. And we checked, we computed such things for translational translations in the target space, which is translation of phi, and translations in the worksheet which change position of phi. So if g hat of phi is 1, then this g mu equals to d mu phi. Actually, people also put factor I here, depending on the definition, but we'll see later how to choose such things. And if it is translation in the target, which is a mu d mu phi, then this integral has indices. It has two indices, and there is this energy momentum tensor, which is d mu phi d nu phi minus 1/2 g mu. Like this. So it can be obtained just by application of this formula. It's called the Noether theorem. I don't know, maybe we can just call this formula Noether theorem. Well, all the statements are Noether theorem. Now I want to talk about what happens in the conformal theory, because it is some general construction which does not rely on conformal invariance in any case. But we have some special situation where it is 2D CFT. So let us try to look at this conservation laws for example, for J. So um, there is what to say it. Let us actually pass to holomorphic and anti-holomorphic coordinates, because originally we work with x1 and x2, and let us now say that there is z, which is x1 plus ix2, and there is z bar, which is x1 minus ix2. Mm. Oh, who can tell what are disease? DZ1 or DZ and DZ bar in terms of dx's, or vice versa. Well, let us first, we can write d1 minus d2 minus I, right? But let us check this. Let us check what happens if we differentiate z in dz. It's yes, it's it's so, and d z bar is 1/2 d1 minus I plus I d2. Thanks. So there is this transformation, but let us also, what can we ask? We can also ask what happens with a metric and with and with epsilon tensor. So we have a dx1 squared plus a dx2 squared, which is a metric. So it will now be 1/2 dz tensor dz bar plus dz bar tensor dz. And there is also a volume form, which is dx1 wedge dx2. But let us maybe go from the other side and compute the volume form for z variables. Dz wedge dz z bar is minus 2i dx1 dx2. So dx1 dx2 equals I over 2 dz wedge dz bar. Or in other words, we can say that it is I over 2 dz tensor dz bar plus minus dz bar wedge tensor dz. So something like we have g, we have omega, and so they have this formulas that differ only by a prefactor and by derivative sign. And we can also construct something like g minus I omega, which will be just a single term. In a sense, it will be a dz tensor dz bar. One is symmetric, another is anti-symmetric. So, but I'm writing this to say the following. So, before going to this homomorphic and anti-homomorphic coordinates, we can notice that there was a current, so we had a topological current, and we have this current. So there was G mu, which is I d mu phi, and there is G mu topological. So let me put here. Let me put here. Let me write this current with the lower index. And this topological current is epsilon mu, or maybe here let us put I, epsilon mu, d mu phi. So if now consider sum or difference of these two currents, G mu minus J mu topological can be written here. So it will be and if we now write all this in terms of homomorphic and anti-homomorphic coordinates, we can see that this tensor has only non-trivial component at when mu equals to z, nu equals to z bar. So let us call this J plus. So this J plus will equal to yes. No, this is correct. Yes. So this will be this tensor has the only component for z and z here and z bar here. So it will be j plus z. Maybe we can put plus on the top. But here's this upper derivative, and the bar component of this field is just 0. So this component will equal to, so we need to lower the index with this metric. So it's inverse metric, so it will be in the factor of 2. So it will be 2 times d. So we can write here that g inverse will be 2 times dz tensor dz bar plus d bar tensor dz. Will be 2 times dz phi. So now if we write equations of motion like d bar phi equals to 0, then we see that equation satisfied by this d plus is d bar j plus equals to 0. J plus we can write just mu, but one component is 0. So so here it's some trivial example because because it's just a scalar field. In a sense, we could do all this just writing it in the components. But I wanted to show somehow that this topological field is this topological current, the existence of this current is a little bit responsible for holomorphicity of the currents. So. So all this can be written in a simpler way because we can work with this z and z bar coordinates from the very beginning. So we can write that this j has so that j that equals to dz phi, I dz phi, and j z bar equals to I dz bar phi. And then naively conservation law would say that d z d z bar jz plus d z j z bar equals to 0. So this is what we expect naively. But in reality, each of these two terms equals to 0. Because it is just d bar of phi, so both of these terms equal to d bar phi. And if we talk about this in different coordinates, like 1 and 2, we will have this topological field, and a subtraction or addition of this topological field just creates us a current which has just one non-trivial component. So conservation law for this current will be either this or this. Okay. So is it? Is it okay?
So you say in other coordinates you have just one.
I'm saying that we can in order to get conservation law which says that something is holomorphic without any observation, without such observations, we could look for the the current which can be added or subtracted from our original current to keep only this component or only this. So.
But the sum is zero comes from the conservation of the non-topological current.
Yes.
While we use the conservation of the topological, we get to the each of the sum.
Yes. Yes. But in principle, we can even forget about this other current. We can just see that in this theory, there are these objects dz phi and dz bar phi, and one becomes holomorphic, another becomes anti-holomorphic thanks to the equations of motion. Because
the topological current is conserved also not on shell, right?
yes, because it's just a statement that two derivatives can be permuted.
So, but this equation, like both of them being zero, is true on your shell.
Yes. So,
Otherwise, them not being zero, I mean, otherwise there's some could be not zero, right?
yes.
Unless there's a minus I in one of those two.
No, what do you mean?
Like you said that the sum dz bar jz plus dz jz bar holds on your shell equal to zero.
Yes.
Because I would expect that in jz bar there would be a minus I that it would also hold off shell. The same like with the topological current.
But it will be precisely the topological current written in different coordinates.
Yeah.
From the topological conservation, we have that these two things have to be the same.
Yes.
And then.
Yes. Yes, essentially, this current has a different sign in the anti-holomorphic part, and yeah, so. Actually, there are dualities which permute this two currents, but this can be done only at the level of quantum field theory. Well, maybe not only. We think. On principle, if you have a solution of equations of motion, we can just change the sign for the part with we can change sign of the anti-holomorphic part, and it will be another solution. So in principle, this duality also holds on there. Okay, but let us think about this. So, are there any questions? So let us think about this phenomenon. It is a general situation in conformal field theory that we have not just usual conservation laws, but we have holomorphic and anti-holomorphic currents. And let us actually look at another example of this. So there is this energy momentum tensor there. So if you don't know how to get this formula, you can watch in the last part of the previous lecture, or just take the definition and try to run this proof of Noether theorem to get such formula with d mu epsilon nu times t mu nu. Mm. Mm. And now let us try to compute this energy momentum tensor in holomorphic and anti-holomorphic coordinates. So t mu nu. Let us compute t zz. It will be dz phi minus what should I subtract here? Will there be any term? Actually, let me maybe put overall 1/2. No. Yes, correct. Because metric has only z bar and z bar z components. So it's just this. And the same for t z bar z bar. And now about t z bar. So this will be dz phi dz bar phi. And now what should I write here?
You have 1/2, then you have 1/2 coordinated,
Yes.
and then
dz.
and then
So let me.
maybe you have 1/2 with
But so concerning. So just two or something more.
But then there's like raise and lower the indices with the metric of
So to yes, so to raise the index, we need to multiply by the inverse metric, which contains 2. So it will be a factor of 2, and it will be dz phi, the bar phi, and plus another such term, because rho goes over z and z bar. Yes. So and this is precisely because of conformal invariance of this theory. So we will see later that, we can see at this moment that this t z bar is a component that equals to trace of t, because what is trace of t? It is g mu nu t mu nu. So it is j z bar t z bar twice, because t is symmetric. At least in this case we see that it is symmetric, but it is general phenomenon. So So in G is Z bar, we can read it from there. It will be 2. So it is 4 T Z bar. So it's a trace of energy momentum tensor, and the quantity which is invariant and the coordinate transformations. So in a sense it is scalar. So and it equals to 0. So this energy momentum tensor is a symmetric traceless tensor. Okay. And it's actually a consequence of the fact that space-time is two-dimensional, because if you compute trace of the energy momentum tensor in for this scalar field, then it will be what a trace trace t, which is t mu. It will be d mu phi d mu phi minus d over 2 d mu phi d mu phi. It is d mu phi because it's a trace of a metric. So it's 1 minus d over 2 d mu phi d mu phi. And this is consistent with the fact that dimension of a scalar field in different dimensions will be different from 1. So because in different dimensions we have integral of d dx d mu phi d mu phi, and this has a dimension d, and this has a dimension of phi, 2 dimension of phi minus 2. So sorry, minus no, this has dimension minus d, this has dimension of phi plus 2. So and overall the dimension should be 0. So the dimension of phi is d over 2 minus 1. So it is dimensionless in dimension 2, and in higher dimension phi is not dimensionless, and this section is not conformally invariant. It's not scale invariant. So
we're saying that the trace of energy momentum tensor is 0 equates to saying that it's scale invariant.
yes, we will see it later, but in general, there always this. So, because we need to write some formulas about this, but let us do it a little bit later. And now let us see what are the consequences of this vanishing of t z bar in 2 dimensions.
So it is a statement that the only conformal theory must be 2-dimensional.
No, there are 4-dimensional and 6-dimensional, maybe. Oh, there are conformal and even topological field theories, maybe in any dimension, in any reasonable dimension, but they contain fields which are more complicated differential forms. It is traceless at the equations of motion, I think, not identically traceless. Mm. And well, example of no, let me think. Let me think. Mm. No, so actually it should be identically traceless. I actually forgot what happens in thermodynamics. Mm, no, it should be identically traceless because it has only first derivatives and equations of motion contain second derivatives. So there is no way to do something like this. But actually, I need to remember what happens precisely.
What happens if I use the first order formalism? Like I
Mm.
introduce an extra field that when it will be the equations of motion gives the basically the momentum of P.
Oh, what?
So the momentum would be P phi times P, and then the equation of motion for P is just P equals d phi, so the Lagrangian would just be d phi d phi.
So you want to kind of integrate d mu phi to something like p mu p nu plus p mu d mu phi, something of this kind.
Yes, exactly.
So this p mu will be of some dimension, like it basically it will have the same dimension as d mu phi, 1.
But is it a theory that in the two, like in the second order formalism, it's conformal? Can you say something about the first order formalism still staying conformal? Because it's clear that when you algebraically go to the equation of motion P, then it's conformal, right? But before applying the conformal transformation, the equation of motion.
Oh, but the action of this theory will be conformally invariant if we transform P mu as a vector.
So it's still conformal.
Yes. But transformation properties should be correct. Oh, example of four-dimensional conformal theory is electrodynamics, for example, or some gauge theory in general. But they are conformal only at the classical level. So on the quantum level, they have beta functions which can vanish if you add some supersymmetry, in a sense, add the fermions, some scalar fields, and so on to cancel everything. No, free Maxwell is conformal only. Free Maxwell is yes, you're right. Free Maxwell is conformal at classical and quantum level because it is free. But if we consider some young mules, in a sense, right in action, S equals to the integral f wedge star f was f being the a plus a wedge a. for some non-abelian field, then it will be conformal at the classical level, but not at the quantum level. And also, if you take Maxwell theory and add some fermion, like in real life, if we add electron, it will become non-conformal. But actually, the whole standard model is conformally invariant at the classical level, except the term of the Higgs, except the Higgs potential. But on the quantum level, it's not, of course. No, because there are non-trivial beta functions, because everything gets quantum corrections. Yeah, but let us see what are the consequences of this vanishing of z bar. So d mu t mu equals to 0 can be written as d z bar t z z plus, so I'm summing over this pair of indices, plus d z t z bar z equals to 0, one equation. Another equation is for the second index equal to z bar, dz t z dz bar t z bar plus d z t z bar equals to 0. So this vanishes, and this this vanishes. So we get that d z bar of t z z equals to 0. So so we have another pair of holomorphic and anti-holomorphic currents. And now let us check why it is true, but it is easy because TZZ is dz phi squared, and the equations of motion for phi is d bar phi is 0. So d bar of this d phi squared is 0. And actually, we see that we can take any power of this d phi, and it will still be holomorphic. So, are there any questions about this? So, what statement? So I'm saying that this is true because d bar of d phi squared equals to 2 d phi. Now, let us actually put arbitrary k here. K d phi to k minus 1 d bar phi. And this is 0 because of equations of motion. But in principle, we see that there are infinitely many tensor charges here. So we have not only some holomorphic current, but the huge algebra, at least in the classical level. Because, for example, at the classical level, we can compute Poisson brackets of these fields and get some Poisson algebra. And then the quantum level, it will be some operator algebra, which will be, in this case, the Heisenberg algebra. So, okay, so any questions about this? Mm. Okay, let us talk about this general phenomenon about transformations that depend on only on z or only on z bar. In a sense, it was called the holomorphic transformations. So we have a transformation. So S of phi plus j epsilon of z phi equals to g of phi plus O of epsilon squared. So there is some transformation that depends on a holomorphic function. And the first example was that z goes to like phi of z. Phi of z goes to phi of z plus epsilon of z. Yeah, thank you. Yes. So there is such an example, and it is a conformal transformation, so it is a symmetry of our action. But there was another transformation. So we were looking at the constant shift of phi, but if we shift it by some holomorphic function, then what happens? So maybe we should put here the bar as well. And well, but here we can formally say that the bar is not transformed, but we can also write transformation of the bar. It does not matter because everything is linear. And we can consider a holomorphic and anti-holomorphic transformations separately.
So after the transformation, you get, don't transformate the bar, you get something that is not more than one the bar than the other.
So what is it again?
So you said I can transform Z and not transform the bar. So Z prime is not no more the bar.
Yes, something like this, but maybe it's better just to write both transformations. The only statement is that they appear well, epsilon of z bar. The only statement is that when we study the first order transformation, they are independent terms with epsilon and epsilon bar, and vanishing of something means vanishing for one term and for the other term. So yes.
So on the first part and the second part.
Mm-hmm. Yeah. So, but it does not have any other meaning apart from that. Everything is linear, and these terms cannot interact because mm, there is no reality conditions for this epsilon, for example.
But there is for phi.
Yes, but we don't have a phi bar anywhere, so we don't know if it is real or not. So we don't care about this. Okay, and now we have this holomorphic transformations, and we know that this is the symmetry. And now we do absolutely the same trick. Let us say that we are considering this transformation with epsilon and epsilon bar. So with z and z bar phi. So since it vanishes for epsilon z bar independent, it means that the result should be proportional to d bar epsilon, d bar epsilon times times some j plus O of epsilon squared. So it's kind of a holomorphic version of Noether theorem. Well, if if we need to add also epsilon bar, then there will be another term with plus d epsilon bar times j bar. Okay, so so this way we can find this components of current, and we also know that this can be integrated by parts, and then when we substitute phi, if we substitute this phi on the equations of motion. And take arbitrary epsilon, it will tell us that d bar j and dj bar equal to 0. So is it clear? So here it's not holomorphic anymore. And here we also need this non-holomorphic transformation. We need transformation with arbitrary epsilon. So we can integrate by parts. So S of phi plus d hat epsilon of z bar phi equals, I forgot S of phi here. Phi plus minus integral d to x epsilon dj epsilon d bar j plus epsilon bar dj bar. Now we can substitute epsilon arbitrary, and since phi satisfies the equations of motion, this should be 0 for any epsilon, because it's 0 for any transformation in general, right? So, these two terms are also 0. So. It should be 0, and so for any epsilon. So d bar j equals to dj bar equals to 0. Right. So any questions about this? Okay. And now if we apply this theorem for so if we apply this theorem for this shift of phi, we will get d and d bar separately. So it is clear, right? Because s of phi plus a equals to s of phi plus integral dA d bar phi plus integral d bar a and d phi plus all of a squared. So this will be j bar, and this will be j. And for conformal transformations, I actually did this computation, but in different coordinates from different point of view. So in principle, we can see what happens if we consider s of phi plus epsilon d phi plus epsilon bar d bar phi. So it will be so all these computations are up to some overall coefficient. So the terms which we get here will be a d of this but actually it is it doesn't matter. We don't need to write both terms because they're equivalent by integration by parts. So to the overall factor, we have this construction. So it is a d of change of phi times d bar phi plus something else. And the other term is equivalent by two integrations by parts. One moves this derivative here, and another moves this derivative there. So so on this continuation of this quality, it will be the epsilon d and d phi plus epsilon d2 phi plus plus d epsilon bar d2 d bar phi plus epsilon bar d bar phi. So there are already terms which actually just one term that I will like on this one because it contains a d of epsilon bar. Other terms contain either epsilon bar or just epsilon, we should think about them more. So there is this one. So what do we have here? We have the epsilon times d phi d bar phi.
The first term is not d bar bar squared, squared.
Hmm?
The first term, no, the previous one, no, the beginning of the test.
Yes, I missed. Yes, thank you. Correct. So this term equals to a d of 1/2 d bar phi squared. Now, what about these terms? Mm. So here we have so this two together are d bar phi times uh, times d of epsilon d phi. So they they can be integrated by parts. Maybe no. Let me think. Let me check if I could do some stupid mistake or so. Probably it is fine.
Are you sure?
Hmm?
The transformation to the second factor is the same.
What do you mean?
When you apply d bar epsilon d phi plus epsilon bar d bar phi.
Yes, of course, because of this argument, we can integrate it by parts twice. So this, yeah. No, actually, no, it is fine. We should just integrate this term by parts to remove this unwanted term with the epsilon, which should not appear, and as a result, we will also kill the term with epsilon, one of the terms with epsilon there, so it will be d epsilon bar d bar phi squared e to x plus integral, so it will be minus epsilon d2 phi d bar phi minus epsilon d phi d bar phi plus epsilon d phi d bar phi plus epsilon bar d of 1/2 d bar phi squared. So these two terms cancel, and this term is d bar of 1/2 of d phi squared. So now we integrate this by parts and combine with this term. So 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 and finally, combine these two terms, get 1/2 integral d to x d bar epsilon d phi squared plus d epsilon bar d bar phi squared. So these are our old friends t and t bar, and there is no t z bar which could appear at d epsilon or d epsilon d bar epsilon bar, I think.
The fact that the two currents get defined isomorphic and then isomorphic separately is related to the fact that we have a larger symmetry, which is the one we said at the beginning.
Yes. So. Yes. But here it's kind. It's it works kind of this way, that if theory has a conformal symmetry, then almost likely, if theory has a scale symmetry, it almost likely has a conformal symmetry. So a scale symmetry shows that its measurement in tensor is 0. There are some arguments which I don't remember precisely. I don't remember in what generality they work, but they say that well, question about vanishing of this energy momentum tensor of trace of energy momentum tensor. So let me think. Oh, if it vanishes identically because of conformal symmetry, no. So in principle, trace of energy momentum tensor could be some derivative of some function. Then the integral of it would be 0. But there are some arguments why we can always redefine it such a way that it is just 0 and not derivative of something. But let me show this general arguments about any theory. So.
My question was about the shift.
Oh, but but it's oh, wait. Which shift do you mean, in the space of phi's or in the space? Yes. Yes. But what was the question?
Well, the question is that, okay, since we know that the currents, those currents are zero dependent, this is related to the fact that we have a larger symmetry, which is not just a shift by a constant.
Yes, and I wrote it somewhere and probably already erased that we can. So did I erase it or not? No, but it's here. So yeah, there is this symmetry, and I computed corresponding current here. So we can shift by homomorphic and anti-homomorphic functions and see what happens when we break these functions. So sorry, one of them should be a bar, this one. Yes. Mhm. Yeah, this works in both directions. If we know that some current is homomorphic and anti-homomorphic, it means that corresponding symmetry can be enhanced to homomorphic and anti-homomorphic symmetry. Or if we have such symmetry, then we know that current should be homomorphic or anti-homomorphic. And it's a kind of a general phenomenon that if we have conformal field theory, then all such continuous symmetries should upgrade to homomorphic symmetries. Basically because generators of these symmetries and generators of conformal transformations form closed algebra. So if you have some generator for example, this constant parameter, we can act on it with some conformal transformation and get something different. Because this current corresponding to this symmetries is one form. So it transforms non-trivially under the conformal transformations. But we will see it later in this relation between short currents and conformal transformations.
So you said that having a conformal symmetry implies having a holomorphic transformation.
Oh, I'm saying that if we have conformal symmetry and we have some continuous symmetry in the theory, then this continuous symmetry upgrades to holomorphic symmetry.
Because you said that they enclose the algebra.
Mm-hmm. Yeah.
So you can.
Yeah. Maybe I actually don't know. Maybe it's possible to invent some topological example. No, but actually I don't know such examples. Mm. So, for example, if you have some theory with Lie algebra, with Lie group symmetry, and then this Lie group, and it is conformal, then it turns out that this Lie group symmetry is actually a fine Lie group symmetry. So, yes. Well, probably in higher dimensions there should. No, in higher dimensions, there is no space for such upgrades, I think. Mm. Actually, I don't know if there are any general statements about what happens if you have some continuous symmetry plus conformal symmetry in higher dimensions. So. Yes. Mm-hmm. Mm. Mm. Yes, finite dimensional, but there are some. There is a momentum vector which differentiates fields, and there is boost vector, but probably it acts in some simple way on this one form representation. I don't know precisely. But And by the way, another observation here is that this conformal algebra currents are actually expressed in a linear way in terms of simpler currents that correspond to this translation symmetry. And this is also a quite typical phenomenon. Then, if you have some theory with extra symmetry, it usually happens that measurement from tensor can be expressed in terms of generators of this symmetry. So, by the way, before going to more general theory of formal invariance, let me show another example of conformally invariant theory. So let me just write the action of this theory. So there is a theory with such action, and the equations of motion of it are d bar phi equals to mu e to the 2 phi. So is it clear? Why it is so?
Is this what's called usually unitarity?
Yeah, yes, of course.
I've always wondered why it was called unitarity, because I don't see unitarity.
Yeah, but this term is the integral of so we have a metric which is dz squared e to the e to the 2 phi, and this is integral mu integral of square root of g d to x, right? So it is the cosmological term. But this term is more interesting because in principle we also have another quantity here. It is square root of g times scalar curvature. It is d d bar phi up to some factor. So if you try to write how is it called, Einstein-Hilbert action, this term will be the total derivative. So it will be proportional to, well, we know that integral of curvature is something like 2 pi times the Euler characteristic. So, and technically we will have a total derivative which integrates to boundary, basically. And it's a question about boundary conditions of phi, so it's not the dynamical term. But if you ask what is this, the answer is the following. So it is quadratic in phi, so it should contain two curvatures, and But this term contains two derivatives, d and d bar. So if you take two of them, and there will be four derivatives. And how to decrease the number of derivatives, we can add here the green function of Laplace operator. So it is the integral over dx, d2x, d2y. Square root of g of x r of x square root of so let me write it like this. Square root of g of y r of y times 1 over d bar something green function of x y. So it is a well-defined object. So it is well, the green function. It can be computed, and these two integrals are also well-defined. The only miracle in this two dimensions is that this expression is local. So it's not expected from the beginning, but this is it. This green function just removes one derivative from each energy momentum tensor, from each curvature, from each scalar curvature. So.
But it's still quadratic.
Yes, of course.
Not
Oh, but it depends on what people call gravity. If you write gravity with some Hilbert action in two dimensions, it will be just this theory with a cosmological term, and it will be absolutely non-dynamical. But the question is, what is the origin of this theory? And the origin is that basically, if you put any CFT in some background metric and compute its dependence on a metric, then on the quantum level, you will have a correction that comes from a measure in the path integral, and this correction will be precisely this Liouville term. So this Liouville gravity appears as how to say it, as an emergent action for metric in the presence of matter fields.
So basically, I take Einstein inverted into dimension, coupled with a scalar field, then I quantize that, and if I quantize that, I have corrections which are gravity.
Yes. So, no, could you say it again?
I take Einstein inverted into dimension, coupled with a scalar field.
Well, but by Einstein Hilbert, you mean that you write just something that counts the genus, or what?
Yes.
Because oh, you can write this, but you can also write it as just a counting factor.
Yeah. So in general, if I just explicit, like put the, for example, G mu, D mu, phi, D mu phi with G D naught field, that's what you mean.
So I'm saying the following, that there is a path integral for example, this free boson d phi e2 minus d phi defined for metric G and the action that depends on phi and this metric G. Action actually does not depend on this metric G. So this can be written as the integral over dj0 phi in some reference metric e2 minus s of phi g0 times e2, I don't remember with which sign and with which prefactor, something like 96 pi, something like this, but I don't remember precisely. It will be d sigma d bar sigma plus mu e to the 2 sigma d to x if g is equal to e to the 2 sigma d0. So yeah, then it means that this integration measure depends on this metric. So if you want to integrate over all possible matrices, you will need, let me think, no, if you want to integrate over all matrices, it will be more complicated because you will need to divide by diffeomorphisms and so on. So you will need to introduce extra fields. But in general, this Liouville theory can be considered either as a theory of a metric which appears in this way, or it can also be used as a theory that removes the excess central charge. So if we want to make some theory invariant under all conformal transformations, we can well we can add Liouville with appropriate parameter. Let us maybe talking about this at some moment later. So for now, I can only say this. Okay, but I wanted to talk just about the classical Liouville. So there are these equations of motion, and let us try to look at this object. Let us introduce T of z equal to d phi squared plus d2 phi. And let us compute its d bar derivative. So it will be 2 d bar phi times d phi plus d2 d bar phi. Right, so we have d bar already. So it is so now use equations of motion. This gives maybe with minus sign, maybe minus. Yeah. So yeah, we will have mu to the 2 phi minus d of mu times d phi, mu e to the 2 phi. So what does it equal to? So we see that there is a holomorphic energy momentum tensor in theory with this action, and it's actually it is actually holomorphic also in the free body case. In a sense, we could put mu equals to 0, and it would still be holomorphic. So the origin of this in the following. Remember that this free theory had a symmetry of translation of a field. We could shift it by constant. And it also had a conformal symmetry. But what if we now combine the two symmetries and adjust parameter of that other transformation to be of the same nature? Like let us adjust that parameter in terms of parameter of conformal transformation. So, namely, if we say that phi, so originally we had phi of x, x prime, phi of z, z bar. It was going to phi of w of z, phi of w of z, w of z bar. And now let us modify it. Let us add here plus 1/2 logarithm of maybe dw over dz, dw bar over z bar. So it is also holomorphic plus anti-holomorphic modulo some details. And now this term transforms in the same way as this term. So it becomes conformally invariant. And there is an exercise to use this generalized conformal symmetry to reproduce this formula for the action. So it will be not so trivial computation because there will be more terms but it is doable. And in principle, it's clear why we have a second derivative in this term, because parameter of this transformation is a derivative of epsilon. So corresponding contribution to the current should also be a derivative of this current, and also from dimensional reasons, because phi has dimension 0 and a derivative has dimension 2. By the way, the fact that we have this equation helps us to write solutions to Liouville equation almost automatically. So we only have some kind of global problems, some questions about single valuedness, positivity, and so on. But in general, this equation is equivalent to finding the solution. Actually, I forgot to tell that if we have this t here, we can reconstruct a solution of the Liouville equation itself. So there is another a simple computation of this kind. Let us compute d e to minus phi. So d2 of e to minus phi. So it will be d of minus d phi e to minus phi. So this will be d phi squared minus d2 phi e to minus phi. Right? So the equation itself is d2 e to minus phi equals to t of z e to minus phi. So we have this equation, and we have another equation that d bar t equals to 0. So to solve this equation, we need to choose some meromorphic or holomorphic function, and then construct and then solve this linear equation. And after we solved it, we have two solutions, and we have two solutions of anti-holomorphic one, and we need to combine them as some bilinear combination, and then compute metric. So, for example, if t equals to t bar equals to 0, a solution of this equation is that e to minus phi equals to, so we have 1 and z in one case, and 1 and z bar in the other case. So let us take this combination, 1 plus z times z bar. So if you now compute the coefficient inside the metric, which is e to the 2 phi, it will be 1 over 1 plus absolute value of z squared. Or we can do the same with minus. So it's Fubinish 2D metric. And in general, why people call this gravity, because it's equation describing metric of positive curvature or negative curvature, but of some constant curvature. So it is similar to the usual gravity, but the usual gravity becomes topological, and it is not responsible for constant curvature anymore. Okay, so maybe that's all for today. Are there any questions?
We specify T.
Mm-hmm. Yes, so we have differential equation. So the question is, of course, can you solve this equation or not? Because if there are three singularities, it's solved in terms of hypergeometric functions. If there are four, then usually it's not solvable. It's related to classical conformal blocks and so on. But if you have this solution, you can construct metric. Okay, so see you on Monday. Hmm? Ah, but it's not a problem, maybe.